Ladies and gentlemen, we present you Jember Sumringah Traditional Dance by Sanggar Tari Hastarini.
Kami persembahkan penampilan tari pembuka dengan judul Jember Sumringah oleh Sanggar Tari Hastarini. Beri tepuk tangan yang meriah.
Suaranya men, suaranya tidak, musiknya tidak terdengar.
Assalamualaikum warahmatullahi wabarakatuh.
Good morning, ladies and gentlemen.
Selamat pagi dan salam sejahtera untuk kita semua.
The Excellencies, Rector of the University of Jember, Dr. Insinyur Iwan Taruna M.Eng.
Yang terhormat Rektor Universitas Jember, Bapak Dr. Insinyur Iwan Taruna M.Eng.
The Honorable Advisor of ICCGANT Research Group and President of INACOM, Profesor Dr. Andes Slamin, M.Com, SC, PhD.
Yang kami hormati Penasihat ICCGANT Research Group dan Presiden INACOM, Profesor Dr. Andes Slamin, M.Com, SC, PhD.
The Honorable Chairman of ICCGANT Research Group, Profesor Dr. Andes Davik, MSc, PhD.
Yang kami hormati Ketua ICCGANT Research Group, Profesor Dr. Andes Davik, MSc, PhD.
Our invited speaker, Profesor Dr. Basuki Widodo, MSc from 10 November Institute of Technology, Indonesia. Dr. M. Venkatachalam from Combinatorics Arts and Science College, India. Profesor Adil Bagirov, PhD from the Federation University Australia. Dr. Joe Ryan from School of Electrical Engineering and Computing, Australia.
Yang kami hormati invited speaker Profesor Dr. Basuki Widodo, MSc dari Institut Teknologi 10 November Indonesia. Dr. M. Venkatachalam dari Combinatorics Arts and Science College, India. Profesor Adil Bagirov, PhD dari Federation University Australia, dan Dr. Joe Ryan dari School of Electrical Engineering and Computing, Australia.
And of course, we would like to welcome all of our guests and participants for today's agenda.
Serta hadirin yang berbahagia.
First of all, let us express our gratitude to God for the blessing and the guidance given to all of us, so we can come and join this event without any obstacles.
Marilah kita bersama-sama panjatkan puji syukur kehadirat Tuhan Yang Maha Esa, karena atas limpahan rahmat-Nya kita dapat menghadiri acara The Fourth International Conference Combinatorics, Graph Theory and Network Topology, ICCGANT 2020.
Ladies and gentlemen, the following agenda for the second conference are: first, opening; second, singing Indonesia National Anthem, Indonesia Raya and Hymne UNEJ; third, prayer; fourth, speech from the Chairman of ICCGANT Research Group; Fifth, opening remarks from Rector of the University of Jember. Sixth, photo session, and the last is closing.
Hadirin yang berbahagia, berikut adalah susunan acara pada pagi hari ini. Acara pertama adalah pembukaan, kemudian dilanjutkan dengan menyanyikan lagu Indonesia Raya dan himne Universitas Jember, kemudian dilanjutkan dengan pembacaan doa, sambutan Ketua ICCGANT Research Group, opening remarks oleh Rektor Universitas Jember, foto bersama, dan diakhiri dengan penutup.
Ladies and gentlemen, the following agenda is singing Indonesia National Anthem, Indonesia Raya, and hymne UNEJ.
Acara selanjutnya adalah menyanyikan lagu Indonesia Raya dan himne Universitas Jember. Kepada yang bertugas disilahkan. Hadirin dimohon berdiri. Menyanyikan lagu himne Universitas Jember.
Semua bersama
Hadirin dipersilahkan duduk kembali.
Ladies and gentlemen, the following agenda is prayer that will be led by Dr. Hobri, SPD, MPD.
Acara selanjutnya adalah pembacaan doa oleh Dr. Hobri, SPD, MPD. Yang terhormat Bapak Dr. Hobri, SPD, MPD, disilahkan.
Assalamualaikum warahmatullahi wabarakatuh. A'udzu billahi minasy syaithanir rajim. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Innal hamdalillah nahmaduhu wa nasta'inuhu wa nastaghfiruh. Wa na'udzu billahi min sururi anfusina wa min sayyiati a'malina. May yahdihillahu fala mudhillalah wa may yudlilhu fala hadiyalah. Alhamdulillah, indeed all praise is due to Allah subhanahu wa ta'ala. We praise Him and seek His help and forgiveness. We seek refuge in Allah from our soul evils and our wrongdoings. He whom Allah guides, no one can misguide, and he whom He misguide, no one can guide. Wa ashhadu an la ilaha illallah wahdahu la syarika lah, wa ashhadu anna Muhammadan abduhu wa rasuluh. I bear witness that there is no God except Allah subhanahu wa ta'ala, alone without any partners. And I bear witness that Muhammad is his servant and messenger. Allahumma inna nas'aluka salamatan fid din wa afiyatan fil jasad wa ziyadatan fil ilm wa barakatan fil rizq wa taubatan qabla al maut wa rahmatan indal maut wa maghfiratan ba'dal maut. Allahumma hawwin alaina fi sakaratil maut wan najata minan nari wal afwa indal hisab. Ya Allah, you are peace, and all peace is from you, and all peace written to you. In conjunction of the 4th International Conference on Combinatorics, Graph Theory, and Network Topology 2020. Give us among those whom you guide. Grant us health and pardon among those whom you grant health and pardon. I beg you to make my asking you best and my supplication best. I beg you the best success, the best work, the best reward, the best life, and the best deed. I beg you to make my scale heavy with reward, to make me strong in fight, to rise me in rank, to accept my prayer, and to forgive my sin. Rabbana zalamna anfusana wa illam taghfir lana wa tarhamna lanakunanna minal khasirin. Rabbana atina fid dunya hasanah wa fil akhirati hasanatan wa qina adzaban nar. Wa adkhilnal jannata ma'al abrar ya aziz ya ghaffar ya rabbal alamin. Subhana rabbika rabbil izzati amma yasifun wa salamun alal mursalin walhamdulillahi rabbil alamin. Summa assalamu alaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Ladies and gentlemen, the next agenda is speech from Chairman of ICCGANT Research Group. We would like to invite Profesor Dr. Andes Davik, MSc, PhD.
Acara selanjutnya adalah sambutan oleh Ketua ICCGANT Research Group kepada yang terhormat Profesor Dr. Andes Davik, MSc, PhD, disilahkan.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam sejahtera untuk kita semua. Om Swastiastu, Namo Buddhaya, salam kebajikan. Alhamdulillah wa syukurillah wala haula wala quwata illa billah, amma ba'du. Your Excellency, Rector of the University of Jember, Bapak Dr. Iwan Taruna M.Ing, Honorable today's invited speaker, Associate Professor Joe Ryan from the University of Newcastle, the Honorable President of INACOMS, Profesor Dr. Andes Slamin MCom SC PhD, and all the organizing committee of the fourth International Conference on Combinatoric Graph Theory and Network Topology, and of course all the lovely participants who are joining in today's cloud meeting conference. First of all, I should thanks to all of you, to participants who from yesterday who already joined with us either in the plenary session or in the parallel session. This conference organized by ICCGANT, which has been 4 years ago, and now this year is the fourth international conference of ICCGANT. We have at least 150 participants and 8,500 speaker in the plenary speaker. They come and join with us through online and webinar format conference, and they have some of them share their current research either in combinatorics or in applied mathematics, as well as in information system. I believe this conference give a lot benefit to all participants, not only of the lecturer as well as a student, and I see in the conference participant some of them from a teacher and practitioners. The conference aims to bring the current research and to disseminate to other researchers such that we aware that there are a lot of progress in the research, especially on combinatorics. Today is the second day of the conference after having plenary session. We will welcome Associate Professor Joe Ryan first as an invited speaker from Australia, and later on Professor Slamin and other invited speaker as well. And in the afternoon time, we will have again a parallel session. I believe you still able to join with this conference, and I believe you will have a lot lesson learned and benefit from this conference for the better and future research. And hopefully this conference is enjoyable for all of you, And again, I should thanks to all of you and enjoy the conference. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Ladies and gentlemen, the following agenda is opening remarks from Rector of the University of Jember. We would like to invite Dr. Insinyur Taruna MN.
Acara selanjutnya adalah opening remarks oleh Rektor Universitas Jember. Yang terhormat Bapak Dr. Insinyur Iwan Taruna MN, disilakan.
Baik, terima kasih. Assalamualaikum warahmatullahi wabarakatuh. Good morning, selamat pagi. Let me to greet one by one to whom I know. Of course, with respect Chair of ICCGANT, Prof. David, and I know also my colleague, Prof. Slamin, distinguished speakers, Joe Ryan, and of course, distinguished. I also see here is the participant from foreign country, ladies and gentlemen, and my dear college researchers, lecturers, professors, students who are active in the field relevant to ICCGANT. It is my great pleasure actually and honor to welcome you at the present conference, which is held by ICCGANT University of Jember. This year we call it as the 4th ICCGANT, our International Conference on Combinatorics, Graph Theory and Network Topology. They take the term of this conference, of course, about research related to graph theory and its application. Ladies and gentlemen, at the moment, we are still in the COVID-19 pandemic era. As we know by yesterday in our country, especially Indonesia, the number of confirmed positive cases is still increased daily and reach about 150,000. For that reason, we do our conference this year is in virtual rooms. We, of course, I of course hope the present activity does not lose its meaning and purpose. Ladies and gentlemen, we know that a conference like this is very essential for us, especially for academician, researcher, since we may use it as media for sharing experience of ideas from the previous our work in research, review, and survey. Usually, after the event, we will have some, what we call it, joint activity like research collaboration or joint writing and anything form our kind of activity that can optimize our abilities and our performance. It is to inform you that the performance of university in Indonesia is right now recognized based on the output and outcome. Therefore, I think ICCGANT doesn't just stop at this conference activity, because we will support ICCGANT to transform being a center of excellence that continues to encourage, because there can be what we call it, we hope can produce anything output and outcome that relevant to the institutional performance. Our commitment to ICCGANT is we will always encourage to be a productive organization. Of course, we encourage its performance to be in line or relevant to the university vision. I think Professor David know very well about this. And what I interesting to ICCGANT is I know that CGANT, I call it as one of the recognized as a university machines that produce publication at Scopus. I know that here is in 2019, the accumulative number of Scopus publication by CGANT member is about 225 articles. Very great. Yeah? And in 2020 has increased more than 100% and totally now becoming about 468 articles. I hope CGANT continue it consistently in the future. Ladies and gentlemen, I don't want to talk about much more about this conference. I just want to say that I believe that our participation in this conference will lead us to accelerate the exchange of ideas and scaling up of good practices about what topics we are talking about today. Because the MC asked me to open this conference, starting by Bismillahirrahmanirrahim, I officially open this conference. Enjoy your meeting and discussion. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Warahmatullahi wabarakatuh.
Ladies and gentlemen, the next agenda is photo session. We would like to invite all of our guests to the stage, and also for our online guests, we would like to ask you to prepare your camera.
Acara selanjutnya adalah foto bersama. Hadirin dimohon untuk mengambil tempat, dan untuk peserta Zoom meetings dimohon untuk menyalakan kamera dan menghadap kamera masing-masing. Terima kasih. Baik, foto bersama akan kami mulai dengan hitungan 1, 2, 3. Baik, sekali lagi mungkin bisa sambil tersenyum untuk peserta yang ada di Zoom meetings. Baik, 1, 2, 3. Baik, freestyle. Oke, baik, 1, 2, 3. Baik, disampaikan terima kasih, dimohon untuk kembali ke tempat.
Ladies and gentlemen, entering the main agenda for today's event, paper presentation by the invited speaker, we would like to invite our moderator. Please welcome Robiatul Adawiyah SPD MSI and Raffiantika M. Prihandini SPD MSI.
Acara selanjutnya adalah acara inti, yakni pemaparan materi oleh para pembicara yang akan dipandu oleh moderator. Kami mengundang Ibu Robiatul Adawiyah SPD MSI selaku moderator dan Ibu Raffiantika M. Prihandini SPD MSI selaku notulen, disilahkan.
Cek.
Okay, thank you very much for the opportunity given to me. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. My name is Robiatul Adawiyah. I am the moderator of this second day of plenary session. I am not alone here. I am accompanied by my friend. Her name is Rafiantika Megahniah Prihandini, who will write all of the important things during this plenary session. I am very pleased to see you virtually and welcome all of you in this wonderful occasion in the 4th International Conference on Combinatorics, Graph Theory, and Network Topology, ICCGANT 2020. This conference is the annual conference which is conducted by ICCGANT Research Group, University of Jember. Okay, ladies and gentlemen, in this second day of plenary session, we will have 3 invited speakers. The first is Associate Professor Joe Ryan from University of Newcastle. The second is Professor David from University of Jember. And the third is Professor Slamin from University of Jember. Before we go on to the presentation of our invited speakers, let me read the regulation of this plenary session. Every speaker has an hour. It consists of 45 minutes for presentation and 15 minutes for discussion. If the audience has a question, you can write the question in the chat box, or you can ask directly to the invited speakers by using raise hand feature in the Zoom. And then I will call your name first, and you can unmute your microphone. Please mute your microphone during this plenary session if you have no importance, and please do not leave this plenary session until this plenary session ends. Okay, now we go to the first presentation of our first invited speakers, our Associate Professor Joe Ryan. Hello, Joe. How are you? Can you unmute your microphone, please? Hello, Joe.
Okay, I think I am live.
Okay, you are the co-host now, and you can share your screen. You can using the share screen feature in the Zoom.
Terima kasih and selamat pagi.
Okay, selamat pagi, Joe. Okay, while waiting for Associate Professor Joe Ryan preparing his presentation, I will read his CV. Associate Professor Joe Ryan is a senior lecturer in the Newcastle University. He is a lecturer in the School of Electrical Engineering and Computing, the University of Newcastle, Australia. His research interest is graph theory and network topology. He has about 93 publications in the Scopus with H-index 12. Okay, for Associate Professor Joe Ryan, floor is yours.
Thank you. I'm trying to make this larger. Okay, how is that? Firstly, I would like to thank the organisers for inviting me virtually to the 4th ICCGANT. I have been to this conference. I was at the first, and I'm pleased to be back. I only wish that I could be there in person in Jember, and I'm sorry I cannot. What I want to talk about today is a new topic. This topic I discovered when I was supervising some PhD students who were working on resolving sets and metric dimensions. When I mentioned this problem to them, they were at the stage of writing up and they did not want any more work. So they wrote up and successfully completed their PhDs. In the meantime, I visited Professor Ralph Classing at the University of Bordeaux in France and showed him this problem back in 2015. And Ralph Classing, myself and Mirka Miller from Newcastle worked on this problem shortly while we were in France. But unfortunately, Professor Miller passed away less than a year afterwards, and we did not do any more work on this problem. And it wasn't until a couple of years later that Florent Foucault met with Ralph Classing at the University of Bordeaux, and Ralph contacted me and asked if I'd done any more work on this problem. I had not, and he suggested that we continue working on it, even though it was a couple of years old. So we did a literary search and we found that nobody else had done this work. And although Florent had not met Mirka, Ralph and Florent asked me if we could include Mirka as an author because she was present at the start of research into this problem. And I happily agreed. Come January will be the 5th anniversary of Mirka Miller's passing away. And I'm sure there are many people at this conference and many people in Indonesia who remember her. And I would like to dedicate this talk to Professor Miller. So, okay, the concept is on distance edge monitoring. First of all, let's start with a vertex resolving set. Many of you would be familiar with this concept. The idea being that you choose some vertices in a graph and you use those to identify all other vertices in the graph by means of their distance from the selected vertices. In this little graph, I've selected the vertices in red, and so the distance from this vertex to itself is 0, and to the other red vertex is 2. From this vertex, it is 1 to that red vertex and 2 to the other. And you can see this is 2, 2, 1, 1. This one here takes 3 steps to get over to that vertex, but only 1 to here. The point is that all of these vertices are identified by a vector. And each of these little vectors, binary vectors in this case, are unique. And so we can use this resolving set to resolve these vertices, to identify all the vertices. So if we can do that, the set that we have selected is called a resolving set. And the idea is to find a minimum resolving set. In this case, this is a minimum resolving set, and the cardinality of the minimum resolving set, the size of the minimum resolving set, is called the metric dimension. So based on that, my idea was, what about an edge resolving set rather than a vertex resolving set? So is this an edge resolving set? Well, the way we check is if we can remove the edge and we change the vector. So for example, if we remove that edge, this vertex can no longer reach the red vertex in 1 step. It will have to go 2 steps. So this vector will change, and so we are able to detect that one of the edges in this graph has failed. In fact, we can even identify which particular edge it is. We know it's that one because it doesn't affect any of the other vertices. So is this a resolving set for edges? Well, no, because that edge that I just removed, this edge here, if we remove that, none of the vectors change. This still takes 2 steps to get either way. This can still get over here in 3 and 1. So this edge doesn't seem to matter. It's not covered. So our set, while it's a vertex resolving set, is not an edge resolving set. But if we take 3 vertices in our set, then each of the vectors are now 3, because there are 3 vertices to check the distances from, and now all of these edges are covered. In other words, if any edge fails, is deleted, at least one of these vectors will change, and that will indicate to us that something has gone wrong, that the edge has failed or been deleted. Okay, so that's the concept. It's almost exactly the same as vertex resolving set, but with edges. So you might think that that's a very simple concept, and it is, but nobody has done this before. In this case, by the way, these 3 vertices are also a vertex resolving set, because all of these vectors are different. It's not a minimal resolving set, a minimal vertex resolving set, because we saw it with 2, but it not only resolves the edges, but also the vertices. That's just a coincidence. We don't look for that in edge resolving sets, because if a vertex fails, then its incident edges will fail, and our edge resolving set will let us know. So all we need to do is cover the edges, and we automatically cover the vertices. Okay, so that's the introduction. Now, some definitions. For a set of M vertices and an edge E of the graph, we let P of ME be the set of pairs XY, where X is in our set M and Y is another vertex in the graph, such that the distance from X to Y in the graph is not the same as the distance from X to Y in the graph if we remove that edge. In fact, it won't be just not equal to, it will actually be less than. Because if you take out an edge, you can't make the distance shorter. You have to make it longer or stay the same. And we're saying it doesn't stay the same if we have a resolving set. So the edge E belongs to all the shortest paths between X and Y in G. And so if we take E out, then X to Y will be a longer path. For a vertex X, if we let MX be the set of edges such that there's a vertex in G with XV being part of this P set, then E is in our set MX, and we say that E is monitored by X. X is the vertex that will change its vector if E is removed. There may be several vertices that will change, but there has to be at least one if that edge is to be monitored. Okay, so a set M of vertices is distance edge monitoring if every edge is monitored by some vertex in the set. And like in the case of metric dimension, what we are after is the smallest distance edge monitoring set, or DEM. Now, we looked at this problem and came up with a couple of theories regarding complexity. In the first case, we looked at VC, which is vertex cover. I'm assuming that everybody understands the concept of vertex cover. It's every vertex in the graph is either in the vertex cover or it's adjacent to the vertex cover. So the vertex cover is less than or equal to the distance edge monitoring set of G crossed with K1. So K1 is a single vertex that's attached to every other vertex, or every vertex in G. So the vertex cover, or the DEM is between the vertex cover and the vertex cover plus 1. If G has radius at least 4, then we can say that they are equal. And that led us on to, as a corollary, that the DEM is NP complete, even for graphs from a planar subcubic graph attached to a universal vertex. This K1 is the universal vertex. So because the problem is NP complete, then we can start breaking it down and looking at some particular cases. And that's where the problem gets interesting. When we start looking at particular cases, we cannot, well, unless P equals NP, we cannot find a general theorem to cover everything. So we start looking at what we've got. Here's a theorem for X in the vertex set of G and E a bridge. E is a bridge. Again, I'm assuming that people know what a bridge is. A bridge in a graph is an edge that, if it's removed, will disconnect the graph. So if E is a bridge, then E must be in the set X for all X in the graph. And it's a very simple proof. We say, let E be the edge between the vertices U and V, then the distance from X to U cannot be the same as the distance from X to V, because X is either in the part of the graph that contains U or in the part of the graph that contains V. But it can't be in both because there's only one edge between those two parts, because it's a bridge. So these distances have to be different. If, let's say, that X is closer to U than it is to V, then V is in the set P of X and E. And if X is in the other side, if it's closer to V than it is to U, then the edge XU is in P. Either way, the bridge is going to be in MX. And that is the same for all vertices in the graph. Now, that's important because if G is a connected graph with at least one edge, then the distance edge monitoring set of G contains one element if and only if G is a tree. And that should be obvious because in a tree, every edge is a bridge. If you take any edge away from a tree, you are disconnecting the tree. You are disconnecting the graph. So every edge is a bridge. So all you need is one vertex in your set. And if any edge is removed, you'll find that the distance from that vertex to the vertex in your set will become infinite, will be undetermined, because the graph will no longer be connected. So that's the case for trees. This, I'm finding this slide hard to read myself because of all the messages that are coming through from the waiting room. I hope you're able to understand it. And I promise to make these slides available to Professor Dafik, Professor Slamin, whoever needs these. Okay, let's carry on with a few more results. If X is any vertex in the graph, let's indicate by L sub ix the set of vertices at distance I from X. Now, I'm not using N for neighborhood here because the neighborhood I would include all vertices out as far as I. What I want are the vertices at I, just in an orbit at distance I, not closer. So that's why I'm using L instead of N. So an edge UV is in our set around X if and only if one end is in Li and the other end, V, is the only neighbor of U closer to X, one step closer to X. Okay, think about that. X is resolving this edge, and so this edge is on all shortest paths. Okay, so X to U must go through V. So U is at distance I, but because we must go through V, then V must be at distance I minus 1. And there's your edge. Now, if this is the case, then we have layers from neighbors of X at distance 1, and then distance 2, distance 3, down to distance I. But there are no edges between vertices at the same distance. And there are no edges in the resolving set. There are no edges to those vertices going further back. So because there are no edges at siblings, at vertices on the same level, there are no odd cycles and there are no even cycles. So there are no cycles, which means we're dealing with a tree, except that it doesn't need to be connected. So what we're dealing with is a forest. So there are no cycles and the set of edges doesn't need to form a connected graph. It does need to form an acyclic graph. And so we have a forest. Okay, so since the problem is NP complete, let's look at some particular graphs. We already started with trees, and that's all trees. That takes in everything from stars, which have vertices of a very big degree, to paths, which have vertices of a very small degree but large diameter. And we found that the size of the set for all trees is 1. Let's go to the other end and have a look at complete graphs. The graphs that are the densest graphs. The size of Kn of a complete graph on n vertices is n minus 1. And here's an example. Here's a little K5 where I've chosen 4 of the vertices, n minus 1 vertices for my set, and not this one. But if you notice, each of the edges is incident with one of the vertices in our set. So that if any of the edges are deleted, the vector will change. If this edge is deleted, then this vertex can no longer get to the vertex in the set in 1 step. It has to go 2 steps. So its vector will change, and that will indicate to us that an edge has been removed. If we try and get away with something smaller, if we try and get away with just 3 vertices, and have 2 not in the set, then this edge is unmonitored. If that edge is deleted, this vertex can still reach all vertices in the set in one go. This vertex can still reach all vertices in the set in one step, and the vertices in the set can reach each other in one step. And so if this edge is deleted, we don't know. It's not monitored. So to monitor all edges, you need n-1 for the complete graph. Okay, let's move along. What about a grid? The grid AB has A rows and B columns. In this case, my little example has 1, 2, 3, 4, 5 rows and 1, 2, 3, 4 columns. So this is G54. And I've started selecting my set by making sure I take 1 out of each row and 1 out of each column. Because there are more rows than columns, one particular column is going to have 2. That's okay, as long as each row and each column has at least 1 member of the set. So I'm going to need at least 5 to cover all the rows. Now, have I covered all edges? Are all edges being monitored? Well, if we look, we can see that edges adjacent to the vertices in the set must be covered. All right. So these edges must be covered, because if that edge is gone, then this one cannot reach that in one step. So any edges that are incident with edges in the set are automatically covered. So that's all of these ones in dark, and down here as well. If that's missing, this vertex can no longer get there in one step. Its vector will change and we will be aware. But what about this one? There, 1, 2, 3. If that edge is removed, it cannot get over here in 3 steps. This edge, if we look at, this vertex, if we look at this vertex, that edge is incident to it, and if it's gone, 1, 2, can no longer get there in 2 steps. If this edge is gone, it can no longer get to that vertex in 2 steps. If this edge is gone, well, 1, 2, 3, it can still go 1, 2, 3. And then 1, 2, 3, 4, 1, 2, 3, 4. It doesn't matter. So this edge is not covered? Well, it is actually, because if it's missing, this vertex can no longer get up to there in 3 steps. So if you're looking at an edge, you must check both end vertices. And in this case, we find that all edges are covered by the little arrangement that I have made. And in fact, our theorem is that the distance edge monitoring set of the grid AB is whichever is the largest from A or B. In this case, A is the largest. There are 5 rows. And B, excuse me, and B is only 4, so we need 5. If A and B are equal, then fine, whichever one it is. So if we had an extra row, an extra column, 1, 2, 3, 4, and the 5th one would go onto the last column and would cover. So that's the case for trees, complete graphs, and grids. Let's go on. Here's a new term for you. You may not be familiar with the arboricity of the graph. The arboricity of the graph, which is just written as ARB of G, is the smallest number of sets into which the edges of the graph can be partitioned such that each set induces a forest. Okay, so you partition the edges so that each one of those sets is a forest, is an acyclic graph that's not necessarily connected, and it's the smallest number of sets that you need. So in a tree, the smallest number of sets is 1, because a tree is automatically a forest. Yes, in mathematics, 1 tree makes a forest. I don't think that's true in nature, not in Indonesia, not even in Australia. But in mathematics, 1 tree. So if you start with a tree, the arboricity is 1. 1 set. If you start with a cycle, you have 2 sets. You take out 1 edge, that's one of your sets, and what's left is the other set, and they are both forests. Well, both trees. Okay, so that's the concept of arboricity. The clique number, I think you know, a clique is just a complete subgraph in a graph. So the clique number is the size of the largest clique, the size of the largest subgraph. Now, for any graph with n vertices and m edges, we have that the distance edge monitoring size of the graph is greater than the arboricity. That's because, as we showed, the set m's are breaking down into forests. And the smallest number in the forests is arb, so this cannot be any smaller. It can be equal or greater. So we have a bound, a lower bound for DEM. It's the arboricity. So DEM is greater than or equal to the number of edges divided by n minus 1, because n minus 1 is the largest number of edges you can have in a forest. Again, your forest consists of 1 tree, but in mathematics, that's okay. And DEM is also bounded below by the size of the largest clique divided by 2. Okay, and you can see that because you can break a clique down. How many sets do you need to break down a complete graph into forests? Okay, and because DEM is a breakdown into forests, that again gives you another bound. So we can choose the larger of these bounds to give us a lower bound for DEM. Now, here's a theorem, and I'm going back to vertex cover now, and a little observation. In a graph G of order n vertices, any vertex cover, and this is the same vertex cover that I mentioned in the slide about complexity, right? Any vertex cover is a distance edge monitoring set, because a vertex cover covers all edges in the graph. It may not be minimal, but it is a distance edge monitoring set. So the distance edge monitoring set is no greater than a vertex cover. It could be less than or equal to, and of course, it's less than or equal to n minus 1, which is the case for the complete graph. So if C is our vertex cover, then for every edge in the graph, there's a vertex in the graph where E is in the monitoring set of that vertex, MX. So our set C, our vertex cover, is distance edge monitoring. Now, if for every vertex of the graph, MX consists of exactly the set of edges incident with X, then M is the distance edge monitoring of G if and only if it's a vertex cover. Be careful, we are not saying that this gives us a characterization of all graphs where the vertex cover is equal to the distance edge monitoring. But we do have some graphs where they are equal. And some of these are important graphs. Here's an example. The complete bipartite graph. A vertex cover, a minimal vertex cover of the complete bipartite graph is the size of the smaller of the two bipartite sets. So in our example here, we have K3, 4. 3 is the smaller partite set. And so we select those vertices. Now those vertices are a vertex cover. They cover every edge. And so they are also distance edge monitoring. If any of these edges is deleted, if that edge is deleted, then this vertex can no longer reach that vertex in one step. It has to go 1, 2, 3. So its vector will change, and we will be aware that the edge has been deleted. Not just aware that an edge has been deleted, we know which edge, because we know that this vertex has the vector 1, 1, 1. This vertex has the vector 1, 1, 1. So does this vertex, so does that vertex. So they are not vertex resolving vectors. This is not a vertex resolving set, but it is an edge resolving set. Because if any edge is removed, say that one, then this vector now becomes 1, 3, 1. And so we know that the edge between this vertex and the second vertex in the edge monitoring set is the edge that's missing. So this set tells us, 1, that an edge is missing, and 2, where it is. So this set is not only a vertex cover, it's also a distance edge monitoring set. As I said, that's not the case for all vertex covers, and it's not the case for all graphs, but it is the case in complete bipartite graphs, which are an important family of graphs. It's also true in another important family of graphs, the hypercubes. This example of a hypercube is Q4, okay? And a vertex cover of Q4 requires exactly half the vertices. As you can see, there are just as many black vertices as there are red ones. So the vertex cover of the hypercube HD is a half of 2 to the D. So in this case, H4, we have 2 to the 4 minus 1, 2 cubed, which is 8. And they are 1, 2, 3, 4, 5, 6, 7, and 8. The 8 red vertices are not only a vertex cover, but they are also a distance edge monitoring set. So your vertex cover will always give you a distance edge monitoring, but it won't always give you a minimal. And DEM is the smallest value. Okay, so we've looked at grids, complete graphs, complete bipartite graphs, hypergraphs, trees. trees. We could go on to the next sparsest set of graphs, which are unicyclic graphs. Let's take the cycle. In the cycle, we cannot have just one vertex in our set. We've already said that if that's the case, it must be a tree. So we must have at least two in our set. Is two enough? Well, for this even cycle, obviously the two edges adjacent to the vertices in the set are covered. Is that edge covered? Well, if it's removed, this vertex can no longer get there in two steps. It has to go around the other way. And this vertex can no longer get there in two steps. It has to go around the other way. So yes, that edge is covered by symmetry. This edge is covered. All edges are covered. Two vertices does the trick. And for odd cycles, we get the same. If this edge is removed, then what? 1, 2, 3 to get to there. If it's still in, 1, 2. So by removing that edge, this vertex can no longer get to that vertex in two steps. It has to go 3. So this edge is covered. That edge is covered. These three edges are all incident with edges in the set. So they are all covered. So two vertices are all you need to cover a cycle. Now, it goes a little bit further than that. If we look at a thing called the feedback edge set, what's the feedback edge set? It has another name that you might be familiar with, the cyclomatic number. I didn't put that on the slide. I can put it in the notes. But the feedback edge set, FES, or the cyclomatic number, is the smallest number of edges that can be removed to leave a forest. Now remember, a tree counts as a forest, a single tree. So if we already have a tree, we don't need to remove any edges. So FES for a tree is 0. And so DEM is FES plus 1, 0 plus 1 is 1, which we know to be true. If H is a unicyclic graph, if it has just one cycle, then you need to remove one edge from the cycle in order to leave a forest, in this case a tree. So we need to remove one, so FES is 1. And so the distance edge monitoring set of any unicyclic graph is 2. Now, this looks like, okay, maybe DEM is always equal to the feedback edge set plus 1. It's certainly the case for trees, and it's certainly the case for unicyclic graphs. So let's look at some other of our favorite graphs that we like to look at this stage. If we look at wheels, we know that we cannot have just one vertex in the set. A wheel is not a tree. So we put down 2, and I've selected this in the middle because this covers all the spoke edges, all the spokes. So that's a very good place to put one of our vertices. We put another one on the rim, then all the spokes are covered. These vertices incident with that vertex are also covered. What about this edge? If that edge is removed, this vertex can still get there in one step. And instead of going that way, it can still get to the other vertex in 2 steps. So the vector doesn't change. And it doesn't change at this end either. It's still 1, 1. So if that's removed, we don't know. That edge is not monitored. So we're going to need more vertices in our set. And we find that if we put them in like so, we have 4 vertices for this wheel. And now all edges are covered. This vertex covers all the spokes, and the rim vertices are covered by these, sorry, the rim edges are covered by the rim vertices. So I'm calling this wheel W7, by the way, because there are 7 vertices. Some people call this W6 because it's based on a 6 cycle. That's very poor, and I wish I could say that there was one way that we would all agree on, but people don't. So when you're dealing with wheels, be sure to define them very carefully so that people know this is either W6 or W7, but they have to know. I'm calling it W7 because the little subscript tends to indicate how many vertices are in the graph. C6 is a 6 cycle. In other words, if it was C6, you'd expect to see 6 vertices in the graph. K33, there are 2 sets, both having 3 vertices in each. So for this one, I chose the number of vertices, and so 4, I'm saying that that is 7 vertices. 7 over 2, we take the ceiling of that, it's 4. If you'd prefer to use the number of vertices in the cycle, that's fine, just put a +1 next to the end. It'll still work, but pick one and stay with it. By the way, paths are also a problem. PN. Many people, myself included, believe that that means a path on n vertices. But there are some people who believe it's a path on n edges, which means there are n plus 1 vertices. Again, that's a problem that hasn't been resolved. I wish it would, because it can only lead to confusion. So make sure when you're dealing with things like wheels and paths that you carefully define what you're dealing with. With cycles and complete graphs, they're okay. There's no confusion. So on our previous slide, we thought, what about if DEMG is equal to FVSG plus 1? What if it's equal to the feedback edge set plus 1? It works for trees, it works for unicyclic graphs, but it doesn't work for wheels. If it does, you would be able to remove 3 edges from this structure and leave a forest. And I don't think you can do it. In fact, I'm sure you cannot. Okay, so that's pretty much as far as I have gotten. What I would like to leave you with now are some problems that, if anybody finds this material interesting, they may like to work on. And as a special incentive, this has 1 paper, the paper by Florian, Ralph, Mirka and myself. So there's a lot of material still to be done. And as a suggestion, I might say, what about something like this? First of all, find the distance edge monitoring set of your favorite graph. It could be the sausage graphs. It could be those trees where you join up the leaves together. It could be any number of other graphs that I haven't already looked at. Don't go looking at all the different trees, banana trees, olive trees, firecrackers. They're all trees, they're all done. But there are many, many other graphs that are not done. Since we just did the wheel, you might like to think about the gear graph. That just came to me and I haven't done it. The gear graph is where we subdivide the rim edges of a wheel. In some cases, it's known as the Jehanga graph. But you can go even more specific than that. You can subdivide the edges and the spokes. You can doubly subdivide the edge, the rim edges, and singly subdivide the spokes, or doubly subdivide both, or totally generalize your subdivision of your graph. None of that has been done. So if anybody is interested, there's somewhere to start. Here's another one. We found out that DEMG is always, oh, sorry, that should be equal to. No, it's not. Always less than or equal to fs plus 1. Well, that is the case in trees. That is the case in unicyclic graphs. That is not the case in wheels. So find out for which graphs this is the case and put them in a special class. Maybe something will be revealed by properties of graphs in that class. Characterize the graphs where the distance edge magic monitoring set is equal to the vertex cover. We already know that complete bipartite graphs and hypercubes are parts of this. What other graphs would fit into that characterization with those? And finally, for anybody that likes playing with graph algorithms, find graph classes where the DEM, the distance edge monitoring set, has polynomial or parametrized exact or constant factor approximation factors. This last part was suggested by Mike Fellows, who's very big on parametrized complexity. Okay, and that is all I have. I'm sorry I didn't make a Terima kasih slide. Allow me to say, Terima kasih, thank you for listening, and I hope you find this research instructive. Thank you.
Okay, thank you very much, Associate Professor Jorayan. Terima kasih. Very nice talk from Associate Professor Jorayan about the distant edge monitoring. For participants who has a question, you can use the raise hand feature, or you can unmute your microphone to talk with Joe directly, or you can write your question in the chat box. Any question? Okay, there is a question from Mrs. Rika Amalia for Associate Professor Jorayan. Okay, Joe?
Yes, I see that question in the chat box.
Okay. What is the original idea of the distant edge monitoring? Is this came from the real problem? Okay, for Associate Professor Jorayan, you can answer it.
Yes, thank you very much for your question. This does have real-world application. If you have a network set up, then one of the things we like to do with the network is check how robust it is, check on its connectivity. The idea of placing what they call PMU, phase monitoring units, on particular vectors is what gave the vertex resolving set its impetus. It's what started from that. And this is just a case of saying, okay, instead of looking at the vertices, whether they're still active or if they are compromised, let's look at the edges. If we look at the edges, we will then see either the vertex has been disconnected from the network, or some of the edges have been compromised. So by looking at this way, we not only find out more about the network itself, but we also find out about the vertices in the network. So I think this is more powerful because it gives us both instructions, looking at the connectivity of the vertices and the edges.
Okay, thank you very much, Joe. For Ms. Rika, is that enough, or do you have any further question?
There's one here from Kiki Sugeng.
Yeah, the next question from Mrs. Kiki Sugeng. Do you think that the characterization of DEMG equal to phase G plus 1 has relation with number of edge in the graph? Okay, for Joe, time is yours.
That's a very good question. Yes, we know that it's true for the sparse graphs like trees and unicyclic graphs. It may well be the case that when you get more dense graphs that this will not be the case, and so we're only looking at something very small. But wheels are fairly sparse graphs. They have only twice as many edges as there are vertices, so they're not very dense, and it's still not working there. And it may be that there are different bounds come along. We have discovered that 5 times FES minus 5 is an upper bound, we think, for all graphs. Okay, 5 times FES minus 5. So somewhere between FES plus 1 and 5 FES minus 5 is going to be the true upper bound. It's not FES plus 1. We know 5 FES minus 5 does work, does something smaller work. Or do we characterise those for which each one of them work? All good questions, none of which have been studied, all waiting to be picked. Some juicy fruit here.
Okay, Bu Kiki, do you have any other question? Maybe you can ask to Joe Ryan directly.
Yeah, thank you. It's very nice presentation, Joe. I think this is a very interesting topics that we can do more. Yeah, I'm just thinking about like the number of edges may be like very, what you call it, close to the number of vertices. So it's very, very sparse, but yeah, we don't know. So we need to do more research about that. But anyway, thank you very much. Nice to see you again.
Yeah, thank you, Kiki. Good to see you again. And I like your question. I think that superlinear or even quadratic graphs might prove to be problematic, especially things like multipartite graphs. So they are probably worth looking at. And I haven't done any yet, and as far as I know, neither has anybody else.
Okay, let's do it. Okay, thank you, Joe. Terima kasih.
Thank you. Thank you very much, Bu Kiki. Any other question from the participants? Please, because we still have about 5 minutes. No more question? Okay, thank you very much, Joe. I think all of the participants here have already understood about your presentation about distant edge monitoring. Terima kasih banyak, Joe Ryan. But before we go on to our next invited speakers, I will give a little summary about Associate Professor Joe Ryan's talk about the distant edge monitoring. This is the new graph theoretic concept in the area of network monitoring. Formally, a set M of vertices of graph G is called a distant edge monitoring set if for HE of G there is a vertex X of M and a vertex Y of VG such that E belong to all shortest path between X and Y. When the HE fails, the distance dx y increase that we are able to detect the failure. It turns out that we cannot only detect the failing edge but look at it as well. Okay, thank you very much. Terima kasih for Associate Professor Joe Ryan. Please give a virtual applause for Associate Professor Joe Ryan. Thank you very much. Terima kasih. Okay, now we go on to the second invited speakers in the second day of plenary session of ICCGANT 2020. which will be delivered by Professor Davik, MSc, PhD. I'm sorry. The next talk will be delivered by Professor Slamin, MCom, SC, PhD. Okay, hello Professor Slamin, how are you?
Hello, Abi. I'm fine. Thank you. Hello, Joe. Hello, Bu Kiki. Hello, everyone.
Hello, okay. You are the co-host now. You can use the share screen feature, Professor Slamin. While waiting for the presentation of Professor Slamin, let me read the CV of Professor Slamin first. Professor Slamin, MCom, SC, PhD, is a lecturer in the Faculty of Computer Science in University of Jember. His research interests in graph theory and network topology, and he graduated from Master of Computer Science from University of Newcastle, Australia, and he got the Doctor of Philosophy Computer Science in 2002 from the University of Newcastle, Australia. Now, he is the president of Indonesian Combinatorics Society in ACOMS with the number of Scopus document 73 and the H index 12. For Professor Slamin, floor is yours.
Okay, thanks, Abi. Assalamualaikum warahmatullahi wabarakatuh. Very good morning for everyone, especially our invited speaker, Joe Ryan, and our president of INACOM, Ibu Kiki. Yeah. Since not all participants are graph theorists, so I choose topics which is very classic and old in graph theory, namely graph coloring. And in this topic, in this talk, I will give some definition, introduction to the variation of graph coloring, and as well as derivation and application. First of all, I would like to thank to organizer who invite me to be one of the invited speaker in the 4th International Conference on Combinatorics, Graph Theory, and Network Topology. All right, I will start my talk with some introduction, which is the history of graph coloring. And the second one, I will give some variation of graph coloring. I start with the very old one, vertex coloring, and then edge coloring and other type of coloring. And then in the third part, I will give some derivation of graph coloring, which is actually derivated from graph labeling. And I will end up with some motivation. So everybody who is not work in graph theory will motivate to work in graph theory after that, okay? Now,